All right, for our first volume computation setup, we're going to see how we find volumes for solids that are obtained by rotating a region of the plane about an axis of rotation. So picture in your mind somebody doing a pottery on a wheel, and as the wheel spins, they kind of shape the mold. You can think of the outside of what they're molding for the pottery to be a function. And you have the volume that's going to be held is what's really going to be inside this pot. So in this particular picture, the rotation is happening about the x-axis. So we're spinning our wheel this way, and our function is this particular graph here on the outside. And as this thing spins about the axis, this entire region here is going to form a solid. So we could visualize it as doing this particular piece right here. And so if I'm at a particular value of x, if I take a cross section, what I end up with is a shape that looks like a disk. And so we're going to view this solid as being a bunch of different disks that we're going to stack together and add up. And when we stack them and add them up, that's integration. And so starting from right here where we have disks of radius 0, the radius increases and is going to stop at this line where x is the value of 3. So we're going to keep going, and we'll stop right here, and this is going to be the top of our 3D surface. So really what I'm looking at here is a chopped off sphere. And we want to know what is the volume of this object, where we started right here and we ended there. In order to find this whole volume, really what we need to do is find the area of this cross section. This is a perpendicular cross section through this solid that goes through the point x on the x-axis. So this area we're going to label as A of x. And because this whole thing is being rotated, what we're really looking at is an actual physical disks. And so the area of the disk is always going to be pi r squared. That's the area for any disk. But r itself here is a function of x. And the radius is exactly the value of this curve. So r of x, r, is literally equal to this y function, this square root of 4 minus x minus 2 squared. So when we're computing the volume, v, we end up setting up the integral where x starts at 0 and ends at 3, pi times the radius for each one of these disks, which is just our function y. So square root of 4 minus x minus 2 squared. And because the radius has to be squared in here, we get to square it, dx. And now this doesn't look half bad. Remember the trick that Will keeps talking to us about in discussion? We just need to pull this pi out front. So it'll make things a little bit simpler. So our volume is going to be pi times the integral from 0 to 3. The squares and the square root cancel, and we'll have 4 minus x minus 2 squared dx. And we can just multiply this out, or we can just do the integration straight on x minus 2, because with a constant inside, we get exactly that the antiderivative of x, the derivative of x minus 2 is just dx. So this becomes pi times the integral from 0 to 3 of, well, I should just do it at this point. So I have pi, I'm going to have antiderivative of 4 is going to be 4x. Antiderivative of x minus 2 squared is going to be x minus 2 cubed over 3. And this will be evaluated from 0 to 3. Now, if you're not comfortable going straight from x minus 2 squared to x minus 2 cubed over 3, you can multiply this out, get linear terms, and integrate them term by term. But this does work out. If you just look at the u substitution, it literally just happens. So there's nothing really strange happening here, and it's not that bad of a computation. So now we plug in our inputs. We have pi on the outside. We have 4 times x is 3, so we have 12, minus 4 minus 2 is 2, so 2 cubed is 8. 8 over 3. And then we subtract when we plug in 0. When we plug in 0, we don't get 0 everywhere, right? So we do get 0 here. But I subtract away when I plug in 0 here. And when I plug in 0 here, I get 0 minus 2 cubed, which is going to be negative 2 cubed over 3. I'm trying to be careful to leave all the negatives in so I don't forget any, because it looks like I have 3 negatives, and that's a lot. So I have pi, I have 12 minus 8/3 minus, and then inside here I'm going to have negative 8. So that's going to be a positive 8/3. So I have 12 minus actually 16/3. Pi times 12 minus 16/3. So over 3, this is going to be 36. 36 minus 16 is just going to be 20/3. So we're going to get 20 pi over 3. So that is going to be the volume of a sphere of radius 2 where you chopped off the top quarter of it. And this is how we're going to set up things with respect to x. We're going to go a little bit finer in the next video. So we're going to set this up where we're going to start moving where the axis of rotation is. And we're also going to generate areas that are not necessarily trapped by the axis of rotation. So we're going to put holes inside the disks. And so the shape of what we look at will no longer look like a disk. Instead, it's going to be a washer. And so this method is called the washer method for integration. And we're going to do 3 different setups in the next video. And then the following video, we're going to do washers again. But this time, we're going to spin about vertical axes. And so we'll have to integrate dy. So take a look at the video that you're interested in. And I'll see you on the next one. Bye.